nonlinear PDE.
Okay, well, thank you very much. First of all, I want to thank the organizing committee, not just being the last. I should thank it not just on my behalf, but on behalf of everybody who participated in this conference. I think it was an exciting conference. There were lots of discussions, and there will be a few more. But I also want to take the time to thank the secretaries who did a wonderful job. Miriam is here. She was really extraordinarily helpful. And there was also, I guess, Tova, Larissa, and Meira. So we should thank to all of them. Even, I think they are not here today, but they've done a wonderful job. So,
will take care of your food.
Okay, thank you. Okay, so what I obviously the title of the talk is very general. So what I want to do is to find some remarks which are interesting. So what I want to discuss three things. First of all, the first question is, what is PDE? Namely, is it even a subject? Or is it a collection of subjects? Second question, I would like to ask something about what are the main questions in PDEs? Or are there main questions in PDEs? It's another, are there unifying questions in PDEs? And finally, I'd like to talk, but obviously I will not be able to, I'm sure I will not get there, but anyway, I'll say, I'd like to talk about methods. Again, unifying methods. And in particular, I want to talk about Fourier and geometric methods in nonlinear wave equations. So I think there are all sorts of exciting connections between nonlinear wave equations on one side, the geometry, because these equations that are discussed turn out to have a lot of geometric structure, but at the same time, because these are wave equations, we have to look also in Fourier space, and in Fourier space there are also a lot of geometric things. And finally, sort of, I think what presumably will happen, at least in parts of the next century, is that these things will come together, because I think it's more and more clear that you need methods from both Fourier analysis and geometric methods. Combining this is very hard due to the uncertainty principle, but I think there are already certain ways of doing it. But I'm pretty sure I will not get to that. In any case, let's go to the first question. So when it comes to the first question, is there such a subject, PDEs? There are so many PDEs. First of all, I should contradict Sinai, who said there are very few nonlinear PDEs. That's just not true. There are lots of nonlinear PDEs. You can take an arbitrary function, which depends on coordinates, and it depends also on the jet space if you want, and you generate an enormous amount of PDEs. So actually, the question, unlike the way Misha phrased it in geometry, the question is not to generate more and more PDEs, but rather to find a selection criteria for what are the really, truly interesting PDEs. So that's one thing that I want to talk about. But even if you think in terms of what are the interesting PDEs, there's still a lot of mess, I guess informational mess, as Novikov called it, though it's not of the same type. It's not so much that there are theorems which are not exactly proved completely. It's more that there are zillions of theorems proved about all sorts of equations, and it's not at all clear. I mean, nobody, I think, in partial differential equation has sort of a global view of the subject. And so this kind of informational mess that I want to address, it's the one that really is tied also to the question of unity of PDEs. But during the conference, I thought, so I want to talk about something about about PDEs as some kind of a unified subject. But then during the conference, I realized that the question of unity was not even addressed much here, even though one of the titles of the conference was the unity of mathematics. So I thought maybe I should really sort of take a few minutes and talk about that. So I heard, I don't know if I understood correctly, but I think there were something like 4 different views on mathematics as a whole, which were formulated somehow explicitly or implicitly. So one of them was that mathematics is some kind of formalism. There is a formalistic language, and according to this, we prove theorems, and we will even be able to automatize theorems by the end of next century. And okay, so this is one vision about mathematics that I think I heard. Another one which I heard, which was expressed, I think, more by geometers and algebraists, is that somehow mathematics has to deal only with the most lofty parts of objects in topology and algebra, and maybe representation theory and number theory, and everything else is more of the kind of engineering or chemistry or biology type. So that's another. That would be the second thing. Now the third one, which I think was expressed by Yuval Niemann, which I thought was sort of a very beautiful. He gave a very beautiful presentation about mathematics. Is that somehow mathematics is really central to the physical world, and that physics, in fact, has been geometrized during this century. And it expresses, in a way, sort of the opposite view, that physics is really part of mathematics. I think sort of an interesting, now what was the fourth? I forgot. Anyway, so these are three. So at least there are 3 points. Maybe if I remember the fourth, I'll mention that too. So yeah, there was a force actually, maybe expressed in sort of challenges in analysis, which was also kind of opposite to all the other points of view, which was that we should all go and take all these problems which come up in very complex subjects like chemistry and biology and so on, and we should attack them. But it was not at all clear that there was any kind of mathematical foundation that will allow us to attack those questions as mathematicians. So anyway, one thing I did is that I collected some quotations. So the first quotation is due to Poincaré. I'm sorry for the spelling. So it said, it was a warning at the end of last century that sort of mentioned the fact that mathematics without physics will kind of lose itself, in the sense that there will be all sorts of subjects which will develop, and each one will develop other subjects, and there will be islands after islands after islands, and in the end we'll lose ourselves. And I don't know if I should read it or everybody can read it. Shall I read it? So the combinations that can be formed with numbers and symbols are an infinite multitude. In this thicket, how shall we choose those that are worthy of our attention? Shall we be guided only by whimsy? This would undoubtedly carry us far from each other, and we would rapidly cease to understand each other. But that is only the minor side of the problem. Not only will physics perhaps prevent us from getting lost, but it will also protect us from a more fearsome danger, turning around forever in circles. History shows that physics has not only forced us to choose from the multitude of the problems which arise, but it has also imposed on us direction that would never have been dreamed of otherwise. What could be more useful? Now, I'm sorry?
This word music.
Right. Yeah, that's true. So question, I mean, I think it's a very interesting warning for Poincaré, and I think it turned out to be true. I think to a large extent, we really don't talk too much. We talk about particular subjects. We don't really talk about much about unity. Anyway, this was one. I don't completely agree with Poincaré. I think he tells us too much that somehow we should really follow physicists. That's probably not what he meant, but in any case, it might lead that impression. Now, there is another comment which I find sort of the opposite to a certain extent, which is this unreasonable effectiveness of mathematics in physics. So, from the point of view of Poincaré, somehow if we just follow mathematics, development of mathematics in itself, we will get lost. For Neumann or Wigner, said the opposite point of view, represent the opposite point of view, that on the contrary, it's exactly mathematics that gives unity in physics. And in the end, physics will be only understood from a mathematical point of view. So these are two completely different points of view, I find. And somehow, I think we should all think about it. Now, there is another interesting comment due to Einstein. The Lord is subtle but not malicious, which means that somehow mathematics should, that the kind of physics or the kind of mathematics which comes into physics is really not only simple, but also it's both simple and beautiful, I should say. Okay, so anyway, these are three quotations. Now, question: can one put them together? So here is a sort of a funny attempt to do that. This is a, I don't know, this is an impressionistic view of Plato's cave. I don't think you can see very well here. These are the Greeks looking at pictures on the wall. The pictures on the wall are supposed to represent the shadows of the ideal world. The prisoners cannot really look outside at all. And, well, everybody knows that. Now, of course, in the modern view of this picture is this one. There are all these physicists and mathematicians sitting around and looking at all these equations and trying to make sense of them. There is a, if they could see, I mean, they all have, I think, at least some of the physicists have told us, like Yuval Niemann, that if they could see outside, if they could see actually the real objects, which are mathematical objects. So this is supposed to be the mathematical world. Again, it's a very naive picture, but somehow the idea would be that there is some kind of region of this mathematical world which is supposed to be the final theory, so to speak, right? And the final theory has different degrees of connections with different theories, geometry, topology, algebra, many other PDEs, and so on and so forth. Of course, again, this picture is really silly in many respects. I'm sorry?
Where is analysis?
The analysis, combinatorics, and so on and so forth. I just forgot to put them. Let's put it that way. There is, of course, analysis right there, very close to PDEs and geometry. Okay, forget about this. I just want you to give an idea of what kind of things will
Inside sun.
Okay, let me tell you exactly about the sun. So you see, so the sun is supposed to somehow represent the final theory. But of course, this picture is naive not only because of all these islands, which are kind of nonsense, just to give you an idea, but also because we really don't know what the final theory is all about. We don't know. We believe that there is a final theory, but in reality, the final theory could include algebra, PDEs, geometry, topology, whatever, and we have not the slightest idea. What?
Who believes this final theory?
Well, no, I think, for the minute, I think.
Mathematician believes there is a final theory.
I'm sorry?
No mathematician believes.
Well, physicists certainly believe. Some physicists certainly believe.
It's not the final state of mathematics.
No. This is something. This is supposed to be an idealization of something that maybe it exists or not. I don't know. I'm not saying that it exists. I'm just saying that this is a picture that I think puts together both the first quotation from Poincaré and the second quotation from Wigner. Right? Now, I just want to say this is clearly not the picture that I have in mind. I don't think that's the case because, in particular, we don't know at all what will be the final theory. And as I said, all the subject or parts of the subjects could actually be included in the final theory and so on and so forth. If there is a final theory, once again, I don't know. Right? Finally, some words about what we as mathematicians do. Actually, the first one has, I say, uncover the basic laws. This is more what physicists do. But mathematicians were also involved, in particular in this century, somebody like Hermann Weyl. Discover the consequences of the basic laws. This, I think I've mentioned this before. I think there are lots of fundamental consequences which are developed in connection with incomplete theories. By the way, once again, Euclidean geometry is also an incomplete theory. It is an incomplete theory of the world, but it had huge impact even though it was incomplete. And there were many other examples like this. The Fourier analysis, for example, was also developed as a consequence of Newton's laws, in trying to understand Newton's laws as applied to certain specific problems. And it led to a language which plays a fundamental role in physics. The same thing happens with Lagrangian theories, which were developed as a consequence. I mean, in terms of trying to understand the Newtonian mechanics, and it led to fundamental, it led to a fundamental language in modern physics and so on and so forth. And finally, develop all other branches of mathematics. And here's a joke. They are all equal, but some are more equal than the others. I think everybody, we all have our prejudices. So anyway, so these are take this as just a joke, but I think it has it's more than a joke. I think it has something to do with a subject that I wanted to talk about, which is partial differential equation. Is there any kind of unity to partial differential equations? Well, of course, you can abandon unity and say everything. There are all sorts of equations coming up in all sorts of areas. Let's study them and forget about the unity. But nevertheless, I think you can find some unity in partial differential equations if you look at the degree to which the particular equations are connected with fundamental laws. So let me make a few words about this. First of all, I want to start to present partial differential equations very much like Gromov presented in his first lecture. Good problems in geometry, starting from very, very simple principles. So the simplest, I would say, by far the simplest mathematical object we have is Euclidean space. You have Rn, the Euclidean space, and of course you have an operator associated with it, which is a Laplacian, and the Laplacian turns out to be the simplest possible operator you can write on Rn, which is invariant under the group of rigid transformation of Rn. And as a consequence, it has deep impact in all sorts of areas of mathematics, including even number theory, as we have seen. And I'm sorry.
You have misprint.
Oh, I'm sure there are. Yes, heat operator. Oh, Schrodinger. Yes, yeah, because my wife made these slides, and of course she didn't know what. Okay. So you have the.
It is first decade of next century.
Right. I cannot fix it directly from here. Right. So. Once you have the Laplacian, you can look, of course, at the heat operator, which also plays a very important role in geometry and, of course, in physics. And then you can also have the Schrodinger operator formed in this way. But you can also do the next step, which is to take second time derivative. It appears here, second time derivative plus the Laplacian. Now, so this is another equation which depends on time and which is naturally connected with the Euclidean space. But now, sort of one of the things that was discovered in this century by Einstein and Minkowski is that this has a deeper geometric meaning. This operator, which is the wave operator, has a deeper geometric meaning. Namely, it's connected to the Minkowski space. So actually, this operator in Minkowski plays exactly the same role as this operator plays in the Euclidean space. And there is a whole new world here, which is a Lorentzian world. And again, I mean, I think I'm boring by repeating myself. I think it has the same right to exist as this one. So anyway, let's go on. The next step is how do you go further? What are the equations you can write? Of course, you can take now either Riemannian or a Lorentzian metric and generate the same type of operators. In fact, formally they are defined, of course, in the same way. This is a Laplacian corresponding to a Euclidean metric, in other words, a Riemannian metric. And this will correspond to the same operator, to the same object, but now G is a Lorentzian metric. So one is, of course, the Laplace operator, the other one is a wave operator, and they look the same, but of course they are fundamentally different objects in terms of their properties, especially if you go to analysis. Okay, so how to generate interesting PDEs? So the next question is how do you go further from this? And again, I think this was a question that Misha addressed also in the first lecture, so I'm just trying to say that something similar can be done with PDEs. The obvious way to do it is to use the variational principle. So here is the variational principle gives a whole new set of interesting objects which have the symmetries of Minkowski or Euclidean space, but have also additional symmetries, which come up through the Lagrangian. And of course, the Lagrangian, I said it before, the variational principle is connected either with Lagrangian or with Hamiltonian. There are two ways of looking. One is Lagrangian, formally the other is Hamiltonian. They give sort of different, I'm sorry about this misspelling also. They give different way of generating interesting partial differential equations. The Hamiltonian corresponds to Newtonian mechanics to a large extent, Schrodinger equation and so on and so forth. The Lagrangian is the one that corresponds to the Lorentzian geometry. Right? And of course, it comes up in field theory, in classical and quantum field theory in a big way. So these are These are, I think, so this gives you a large set of interesting equations. I should say it's very similar to what happens in ordinary differential equations, where there are many, many ordinary differential equations, but the ones which are considered most fundamental are the Hamiltonian ones. So I think these ones are exactly the analog, especially these, are exactly the analog of Hamiltonian systems of differential equations in mechanics. And of course, the Hamiltonian structure, as you know, it's extremely rich and has led to all sorts of advances, particularly whatever is called symplectic geometry is intimately tied to the Hamiltonian structure. And I think many people here would agree that the symplectic geometry is definitely a very fundamental part of mathematics nowadays. So let's go on. The next interesting thing to say is that symmetries of the Lagrangian lead to all these conservation laws, which are so much discussed, have been discussed so much here in connection by both Bourgain and in connection with turbulence and so on and so forth. They are fundamental objects intimately tied to the equations, the interesting equations that we look at. Okay, so fine. So this is a sort of a short introduction on how to generate interesting equations. Now let's look very fast through some list of equations. So by geometric, I call the ones which really correspond to some kind of Riemannian structure. And main evolution equations, they have the time in. And there are other ways of generating equations, which I discussed. By the way, I didn't discuss all the other ways of generating equations. There are many other ways. So I talked about the Lagrangian structure, but there are other ways of deriving equations. In particular, Navier-Stokes equation is not a Lagrangian theory at all. It's not a Hamiltonian theory. It's not connected with the variational principle. Nevertheless, it's an interesting equation. So there are other ways, which I'll say a few words about those in a second. Anyway, so the geometric, let's start with the geometric problems. Well, there are lots of them, and I don't know, it's one of the confusions of partial differential equations that in some sense, each of these equations which I wrote here is a subject in its own right. So the Cauchy-Riemann equation refers essentially to complex geometry. And of course, you have also an analog in higher dimensions which I didn't talk about. Laplace operator is a whole subject of mathematics which is really harmonic analysis if you want, but it comes up in so many places. It's not, you cannot even place it somewhere. It obviously, as we saw, comes up in number theory and so on and so forth. You have the Dirac operator, which is essentially like taking the square root of the Laplacian, and again it plays a fundamental role, and it plays a fundamental role in topology. And then you have Hodge systems and Hodge theory, which really play, again, a fundamental role in topology, play a fundamental role in geometry, even in algebraic geometry, and so on and so forth. You have harmonic maps, okay, which, again, as far as I can tell, have been used a lot in geometric problems. You have the Young-Mills equations, which has been used, again, just to give random applications. The Young-Mills equations, of course, comes up in topology, in connection with those.
They actually are...
No, but this, I'm talking about, so to each elliptic equation, there corresponds a hyperbolic equation also. If I just take the metric and change it from Riemannian to Lorentzian, I get the field theory. Otherwise, it's a geometric theory. So this is Riemannian. Here, the corresponding metric, I'm starting with Euclidean space here. So the Young-Mills equation, the Seiberg-Witten equation, minimal surfaces, Einstein metric, all these things really are equations, partial differential equations. They have analogs in the Lorentzian case, but of course, the Lorentzian case is not, has sort of a different meaning, and it's obviously more complicated. But the point I want to make here is that each equation, in some sense, forms a whole part of mathematics, and that's sort of one of the difficulties of partial differential equations to even define what it is, what they are. Anyway, so let's look now at parabolic problems also, which also appear in geometry. And again, there are lots of heat flows which are used to define certain metrics, to find metrics which are canonical in Riemannian geometry. And the sort of one example, there are lots, will be the Ricci flow, which is used in geometry. So let's go to the main evolution equations. Sorry. So let's go to the main evolution equation. So first of all, you have the relativistic field. So here, essentially, to every equation which was elliptic, I associate its hyperbolic counterpart, which is now Lorentzian. So you have wave and Klein-Gordon equations. You have the Maxwell equations, which is corresponds to the Hodge system, but it's the one which is used in physics. You have wave maps, which are the exact analog of harmonic maps. You have the Young-Mills equation, but now the real ones, the ones which are Lorentzian. though some people say that the other ones are real. But anyway, whatever. It's not important. Einstein field equations. And by the way, here I come to Einstein field equation. I just want to make a few words that maybe many mathematicians might not realize that the Einstein equations, not only are they, so first of all, let me start by saying that they're absolutely fundamental in a way that no other physical theory is today. I mean, it's one equation which has been checked by recent experiments, in particular the double pulsar experiments, to 1 into 10 to the 16. And there is no other theory which has been tested which has anything comparable to that. Maybe, of course, there is the classic example is electrodynamics. I'm sorry, not electrodynamics, I mean quantum electrodynamics. But another thing that I want to say about the Einstein field equations is that they somehow encompass the best tradition of both mathematics and physics, but mainly mathematics, in the sense that they have, the equations have been formulated as a consequence of first of all, special relativity, which is a geometric theory. It was discovered by Minkowski that it's a geometric theory. It had connections, of course, with the Maxwell theory, but also the Einstein field equations have connections with Riemannian geometry. So, in fact, the main thing was main discovery by Einstein was to change the Riemannian metric of Riemannian geometry to a Lorentzian one, and realize that this is exactly the right framework for the theory. It also contains in it Newtonian mechanics. I think it's an enormously elegant but more than that, it's really a triumph of mathematics. The way it was formulated, it's a triumph of mathematics. Yet I think there are lots of people who don't consider the Einstein equations really as part of. Well, I shouldn't say that way. I should say Einstein equations really has been ignored outside by the vast number of mathematicians. Anyway, let's go on. You go to non-relativistic wave equations. There are the equations of elasticity. There are systems of conservation laws for gas dynamics and magnetofluid dynamics, and there are many other examples. Then there are Euler equations, Navier-Stokes, Boltzmann. I should say about these equations that somehow these equations, like all the other one in the non-relativistic wave equations, they are phenomenological equations. They are not derived from first principles. But nevertheless, they are extraordinarily interesting. So, incomplete.
The Boltzmann equation is not PDE.
I'm sorry?
The Boltzmann equation is not.
Okay, Boltzmann equation is not PDE, but I put it here because it leads to these two equations which are PDEs, right? So, this is one of the things that I wanted to say. These equations are derived under different types of approximations from other theories, which are, so these are macroscopic, but this is microscopic, and. The question, so this, I come to the question of phenomenological equations. How seriously shall we take phenomenological equations? And this is something that I think it's very difficult, and I definitely will not have any time to go into it. But I think it's really a fundamental question for the following reasons. Many of these phenomenological equations are derived under certain assumptions. And then when we do analysis on them, it's not clear that we don't violate the assumptions. For example, when we look for singularities, or we try to prove estimates which show that singularities are not present, and so on and so forth, we may have the difficulty of really sort of reaching outside the realm in which these equations have been derived. And in particular, questions like, for example, breakdown of singularities is really very, very dependent somehow on the model. Anyway, but enough about this. Let me go on. There are other equations which again are derived by approximations from the main ones. And let's take KdV. KdV is a very good example, but these are nonlinear dispersive equations. KdV is a very good example because a lot of people know KdV, but they may not realize that the KdV equation is really not a fundamental equation, even though it has beautiful mathematics in it. Right? So once again, the same sort of story. Equations which are really far removed sometimes can have very, very beautiful structure. And the same thing with Boussinesq and the equations which are derived by Zaharov, and so on and so forth. We have also Schrodinger equations, which I didn't say. These are typically linear. We have equations derived by approximate or symmetry reduction. So this is one thing that is done all the time. You look at the equations, which may be three-dimensional, and you reduce them by looking at symmetries, symmetry reduction. KdV, in fact, is one. Actually, what's beautiful about KdV is that a symmetry reduction, well, it's not just symmetry reduction, but let's say some kind of symmetry reductions can lead to all sorts of extra conservation laws and all sorts of extra symmetries, which, again, we have to understand. Anyway, so here is another example of symmetry reduction. This is a one-dimensional system of conservation law, which has been very thoroughly studied. And I write it as separate because it's really sort of very different from many other equations. Anyway, this, I think, is enough about generalities. Now, let me restrict. I think it's too much generality here. I have to restrict about the equations, some of the equations we have, which to a certain extent are really, well, they're fundamental. Certainly the Einstein vacuum equations are fundamental, but they also, I believe, have really give you a flavor of PDEs as a whole, even though there are lots of differences between these ones and, let's say, Euler equations. But I'll talk more about this in a second. So what are the equations here? So I'm talking about non-relativistic field theories. In other words, these theories which start up with a Lorentz metric. And you look at the Lagrangian, and you derive from the Lagrangian, you derive the equations, right? So the simplest one is nonlinear wave equations. These are equations which have already been discussed by Bourgain. So Bourgain discussed exactly this case. But there are others which I believe are much more interesting and have much more geometric structure. The wave maps, which it's the analog of harmonic maps. So this is a system of equations. The phi i's are the species, different species of the equations. They correspond to maps from Minkowski space to a Riemannian metric. And you look at the variational principle, which is defined in terms of an energy. And anyway, I'm not going to go into details. I have some slides which tell more about these equations. The Young-Mills equations, but again, the Young-Mills equations in Minkowski space, which have this structure. Again, I'll say more about them later on. I don't want to go into any details. Again, the fundamental equation is the Einstein equation, so maybe I should say something here. But I'm looking at the Einstein vacuum equations. In other words, the equations where here the right-hand side, there is no right-hand side. And this is a purely geometric object. It's a Ricci curvature of the Lorentz metric. So you have a Lorentz metric, a manifold, a Lorentz metric. This is a Ricci curvature, and you're just simply looking at the equation Ricci equal to 0. And this equation, as I explained before, is really probably the most perfect of all the physical theories we have today. And it has this beautiful geometric structure. And it's well defined. There is no problem with defining it. The problem is to solve the equation or to understand the properties of solutions of the equations. Now, the other equations are, in a sense, they are all derived from a Lagrangian. So from this point of view, I think they're all interesting. Just like well, other equations, when we look at equations in Hamiltonian mechanics, we don't just look at the Newton equations, we look at all of them. So I think all of them are interesting, but they are also intimately tied to the Einstein vacuum equations. They all can be viewed, all of these things can be viewed as some kind of distant relatives of the Einstein vacuum equations. In fact, this one is not so distant. This one is obtained by a symmetry reduction, by making a symmetry. So the wave maps are intimately tied to Einstein vacuum equations. And the beauty of having all of them around is because Einstein vacuum equations are enormously complicated. And I think it's extraordinary. I think it will be a big mistake to try to isolate the Einstein equations and forget about the other ones, because they have very similar structure at different levels of difficulty. This is the easiest. This is, well, these two are equally hard somehow. And then there is the Einstein vacuum equation, which is much, much harder, but which is related to 2 and 3. Okay, so these are the equations I want to talk about. But now I will talk about a classification which, again, is much more general than just those equations. And it has been sort of alluded to, but I want to make it a little more clear what it means. So there are, you see, so I'm referring now to the equations on the previous slide, but again, I'll make more general comments. You see, the basic equations have conservation laws, which are whatever comes up from symmetries of the Lagrangian. They correspond to symmetries of the Lagrangian. And usually people look at the energy and may wonder why, because there are other conservation laws. But the energy is really the only one that gives you an a priori bound, tells you something, that the solution has to have a certain amount of regularity. All the others don't do that. And in fact, all the others really locally correspond to the same kind of information which you get from the energy. But they will not be able to give it to you. So anyway, So the energy is a fundamental thing, and unfortunately, there are no other, typically, there are no other conserved quantities, and I think Bourgain has talked a little bit about it, and therefore, that's the only thing we can use. So what we do when we classify equations is to compare the strength of the nonlinearity, which I call n, to the strength of the conserved quantity. And you divide the equations into three parts: subcritical, critical, and supercritical. And of course, the critical one is a dividing line. The supercritical is when the nonlinearity is far stronger than the energy. By the way, this is a fact which happens only in partial differential equations. It's not true for ordinary differential equations. If you have a Hamiltonian with positive energy, of course I assume that the energy is positive. I'm sorry, I should have said that. The energy is positive. If you have a Hamiltonian with positive energy, you automatically have sort of subcritical theory. I'll talk more about this in a second. Now, how do you get the strength of the nonlinearity? You get it by a scaling argument. And again, scaling argument came up in many talks, so I will say maybe a few words, but I don't want to go too much into details. But let me say what are the expectations. I shouldn't call them conjectures, but rather expectations. So and these are sort of very, very general. It's not just one equation. I mean, people may have the feeling that there's just Navier-Stokes, and there are all sorts of separate discussions, Navier-Stokes or the wave equation or Schrodinger equation and so on. These are very general. The subcritical, so there is always this kind of tension between the nonlinearity, the strength of the nonlinearity, which you can measure. It's very simple to measure by a scaling argument, and conserved quantity, the conserved quantity, and unfortunately, again, the only conserved quantities we have are the physical one, the energy, typically. Now, it happens, so now what you do is that in the subcritical case, when the energy prevails, we expect global regularity for all data. So again, it's a general, when you hear about, there are all sorts of results about global regularity, they all typically enter into this category. Expect global regularity for all data. Of course, there are other situations, I should say. One should be very, very careful to see what, I mean, when we talk about this definition of subcritical, critical, and supercritical, you have to be careful to see that the energy is indeed the only conserved quantity which gives you a priori informations. So for example, in KDV, you have infinitely many conserved quantities, and there are some which give you a lot of a priori conservations, and therefore you should use those for understanding this. Okay? Right? So this makes sense only if you don't have any other additional conserved quantities. The same thing happens with the Euler equations. This was discussed in 2 dimensions. You have an additional conserved quantities, not just the energy. And therefore, the issue of criticality in two-dimensional Euler equation is very different. You don't measure relative to the energy, but relative to vorticity. In fact, the infinity normal vorticity. Okay, so with this in mind, essentially all equations, so here I come up to this kind of generality. I mean, what can we say generally about PDEs? This is sort of a very general picture about interesting PDE, interesting nonlinear PDEs, I should say. It's of course true only, I mean, it's an interesting classification only for nonlinear equations. Okay, in the critical case, we expect global regularity for all data. But in most cases, I say, because there could be exceptions, and again, I'm not going to go into it, but there could be exceptions for this. This critical case is usually where a lot of modern actions in PDEs takes place. In elliptic equations, I should say, this story is pretty well understood. However, in elliptic equations, very often you have a maximum principle. And again, the maximum principle is like a conserved quantity, and it changes the picture altogether. And therefore, very often you find supercritical theories, so-called, which can be solved in elliptic PDEs because you have this additional thing, this additional invariant which comes from the maximum principle. You don't have this in this evolution equation, in particular in hyperbolic equations. And finally, supercritical, you expect global regularity for small data, and this is, I think, a fundamental result to prove, and expect large data breakdown. So large data in principle breakdown, not small data. So from a certain point on, there is a phase transition. Again, you start getting breakdown in this case. Right? There is another type of phase transition, but there is a phase transition. Then understanding somehow that phase transition is also, I think, fundamental. Anyway, let me go on. And why is this question? So I claim that this is sort of the fundamental question, the main fundamental question in partial differential equations, insofar as it's so general, so to speak. General, of course, not in the bad sense that Gromov had in mind, but in the sense of interesting equations. Right? I'm not talking about, there are stupid equations where breakdown comes up immediately. That's not the point. Right? Here you have a structure, and you want to understand the breakdown relative to this structure. Anyway, so what are the issues concerning with breakdown? Well, first of all, you have to understand you want to understand the character of breakdown, but more important, especially if you are talking about fundamental theory like general relativity, you want to, a breakdown in a fundamental theory is a very serious issue. It tells you that somehow the physical, it tells you if you reach a breakdown, you reach the limits of a fundamental theory like general relativity. So you start worrying then about introducing quantum gravities and so on and so forth. But also it has a lot of practical importance, and we saw in the previous discussion, a breakdown really has sort of serious physical consequences. So it's not just a mathematical problem. It's I think it's a general scientific problem, but it can be addressed in mathematical terms. It's one of those questions that can be addressed in mathematical terms. Anyway, so we expect large data breakdown, and in that case, the issue is also one: can we extend the solutions past the singularities? Right? Okay. Now, how much time do I have?
Oh, 5 minutes.
Okay, so not much, but I'll finish maybe with some. All right, so these problems are incredibly difficult. And of course, it makes no sense to talk about them in generality. Once you have this picture, of course, you go to each particular equation and try to understand that particular equation. So from this moment on, I will only talk about nonlinear wave equations. And you can sort of address a different question which is connected. So once you have a sort of a very big problem which is essentially unsolvable with modern technology, the only thing you could do is, of course, to try to find some somewhat simpler problems which are a little more, which are reachable somehow, and which you hope that it will lead you to understanding the big picture. So one way to look at the question of global regularity is to go to the question of well-posedness. And I'll tell you in a moment what this S critical is. But for the moment, what I want to say is that those four equations I talked about, and more generally equations which come up in field theory, in classical field theory, should be well posed for any S larger than S critical, should be weakly globally well posed for S equal S critical and small initial data. And finally, the general weak solutions corresponding to S less than S critical are meaningless. And I mean this by saying that weak solutions are ghosts. Namely, they exist. So let me address the issue of weak solutions for a second. You can, if you are below a certain exponent, which are called the critical exponent, there is another phase transition that takes place. And the equations become meaningless in the following sense. I mean, this goes back to a sort of very fundamental observation made by Nash, that if you look at the embedding problem in geometry, and if you, there was also a phase transition there, namely, if you look at solutions which are above C1, you get sort of very nice behavior, but exactly at C1, you get something terrible happens to the equations. The equation becomes incredibly loose, and nothing meaningless can be said. And Gromov, of course, has investigated this problem. And there are other situations like this, for example, in connection with the Euler equations, in the work of Scheffer and your work also, which tells you again that if you are below a certain threshold of regularity, somehow the solutions become meaningless. You can take a solution whose start at time t equals 0, starts by being 0, and at time t equals 0 again. So the equation becomes totally meaningless. There are other things like this happening in elliptic theory. There are some results of Zverak, some beautiful results of Zverak, which are also connected with Nash. In fact, I mean, there is the methodology is very intimately tied to what Gromov and Nash did before, which also tell you that before a certain threshold of regularity, the equation somehow disappears. It becomes totally loose. And I think it's sort of a very interesting phenomena that we should understand, and we don't understand at all in the case of nonlinear wave equations. I think results like that should be proved. Anyway, let me show you now what are these critical exponents. So, first of all, what is well-posedness? You look at solutions of an equation which start up with HS regularity. HS regularity, I mean that S derivatives of the solution should be locally in L2. Right? And so I start with a certain amount of regularity, and then I say that the equation is well-posed in HS if I can prove existence of local in time unique solutions. Right? Okay? So, and then the question is, what is the minimum S for which I can prove that? There is also, so this would be the HS which I have there. I'm sorry, I guess I should have this HS. So I'm looking at the minimum S for which I have this type of well-posedness. And I have also a critical exponent, which I have to define in a second. And I'm saying that for any S larger than S critical, I should have well-posedness. Now, let's see what the critical exponent is. So the critical exponent, S equal to XC, S equal to S critical, is an exponent which is invariant under the nonlinear scaling of the equations. Right? So, now, let me say a few words why these things are non-trivial. First of all, in nonlinear wave equations, it turns out that this kind of result, even this kind of result, as large as and as critical, is fully dependent. It's dependent on the nonlinear character of the equations. And in fact, you can write down equations which are not derivable from a Lagrangian, but which have the same kind of structures. The nonlinearity looks, sort of from a scaling point of view, looks in the same way, for which this conjecture is wrong. S will not, you will not be able to go all the way to S critical. There are obstructions, and these obstructions are geometric in nature. And you can only go to S close to S critical if the so-called null condition is satisfied. So null condition is sort of a structural condition, which again I won't be able to say. Structural conditions are nonlinear wave equations, which allow you to go all the way to the critical exponent. But this is based, and here I come to a subject which I will not be able to reach at all, which is this thing with geometry and the geometry of physical space and Fourier space. This null condition is something that you understand in terms of the geometries of the nonlinearity, both in physical space and in Fourier space. There are consequences of this structural condition in both cases. Now, again, this critical exponent, I go back to the classification. You see that subcritical corresponds to critical exponent less than 1, critical exponent equal to 1, and critical exponent larger than 1. These are the wave equations. Subcritical P is less than 5, critical P equal to 5, supercritical P is larger than 5. This is what Bourgain talked about a little bit, so I won't say more. These are the scaling properties of the wave equation. I'm sorry, I guess I should go back. These are the scaling properties of the wave equation, and you see that what you do is you scale the coordinates, the function, and the energy, and you look at the relationship between these, and that's how you get the critical exponent in particular, and how you get the notion of supercriticality and criticality. Here are certain results about the nonlinear wave equation, and again, I won't be able to talk much about it. I go to wave maps. There are, the wave maps are subcritical in dimension 1, critical in dimension 2, supercritical in dimension large or equal to 3. The critical exponent is n over 2. Here the scaling analysis of the equations. I'm not going to go through that. These are some known facts. But let me talk about this result. So there is a well-posedness result for S larger than S critical, and a global well-posedness result for something which is almost critical. By the way, local well-posedness, of course, is connected with the existence of and uniqueness of local solutions. But when S, the corresponding exponent, is critical to is exactly equal to the critical exponent, local well-posedness is in fact global well-posedness. Right? So that's an important distinction. I mean, an important point. So let me talk. I don't think I'll be able to talk about many conjectures. I mean, there's a conjecture here, but I might be able to say a few words about this one, which I think it's one of the most interesting. So what is the point here? We look at the wave maps. There are certain conjectures about global regularity in dimension 2, which I won't have time to go into it. But I want to talk about this type of conjecture, which has to do with well posedness. So here, the conjecture is that if you have the equations, the wave maps equations are globally well posed for small h1 initial data. And to do that, you see, to prove such a result, so this is a result in which I definitely believe, but I think it's very hard. However, it's fundamental in the sense that there is no way to prove the conjectures concerning the regularity of wave maps in dimension 2 without going through this kind of well posedness result. I might turn out to be wrong, but I think that's what happens. In cases when you have additional symmetry, you can do it by other methods. You don't need this one. But in cases where there are no symmetries, which is the one I'm interested in, I think you really have to go through this type of well posedness conjecture. So, what is the point? The point is that the wave maps equation, as you see here in the nonlinearities, you have this Q naught here, which is an expression involving derivatives of I, satisfies a null condition. In other words, it has certain cancellation. So it's a nonlinear cancellation. It's a nonlinear condition, which obviously comes somehow from the symmetries of the original Lagrangian. But as we'll see, maybe I'll say a few words also about Young-Niels. You see in equations like Young-Niels and the Einstein equations that this kind of structural condition is not at all obvious. Anyway, what you want to prove is that in dimension 2, if I start up with H1 initial data, which corresponds exactly to the energy, so these are data of the same regularity as the energy, then we get well posedness. And of course, well posedness means global well posedness because we are at the level of, because of the scale invariance of the H1 norm. All right, so now there are two things which are needed here. First of all, bilinear estimates. So let me say a few words about bilinear estimates. So what are bilinear estimates? These are things which are connected to Fourier analysis. So there is a whole branch of Fourier analysis which goes under the name of restriction theorems. And this was initiated by, I mean, the main result, the first main result in this was a result by Stein-Thomas. That had to do with Fourier analysis, in which the geometry of a particular surface comes into play, the curvature of a surface. You look at the surface and you look at the measure on the surface. You look at the Fourier transform and you look at the operator, which is defined by the Fourier transform. And that operator has properties, remarkable properties, which are not true unless the curvature condition is satisfied. Right? So that's how the geometry came into place in Fourier analysis, so to speak. The geometry of, and of course, this is connected to the fact that if you look at the wave equation, if you look at the characteristic cone of the wave equation, so this is in Minkowski space. If you look at in other words, if you look at the Fourier variables, the symbol looks like this: tau squared minus I squared equal to. So I'm looking at the symbol equal to 0, and this symbol, of course, is concentrated. So this equation is the equation of the corresponding light cone of the wave equation, and the light cones have geometry in particular if they dimension. So I'm looking at dimension n+1. Yes.
Probably you will continue your talk during the discussion.
Okay, very good. Good time.
Because people are with
Some
this.
food.
Some food.
Sorry.
Thank you very much.
This is it.